This lecture is a bit of a uh, maybe misplaced lecture, but before going on and just accepting the completion of our discussion of Pauling's first rule and be able to think about these as ionic radius, I wanted to ionic radii and hard balls and throwing them into these crystal structures and space groups. I wanted to just go over the concept a little bit about how you could actually measure this. And, it's not too useful a concept if we can't come up with sort of measurement of some sort of these atomic radii. And it turns out that, of course, you've seen tables of these probably, and so you know it's possible. But it's not clear because I'll give you a quick example here. Let's suppose you say, fine, what we can do is we'll measure lattice constants. So we have X-ray, and that seems like a pretty good thing. And in cubic materials or other materials, doesn't matter, whatever. We'll measure the lattice constant in a particular direction. Maybe it's if it's cubic, it's A. Maybe in some cases we have to measure A1, A2, and C. Whatever the case, blah, blah, blah. We can measure these things exactly, and if we have two elements, to minimize them, let's suppose I have, like in our last example, I have zinc and sulfur in one, then I can, assume, well, I'll find another binary compound, like with two elements in it, and that would be, let's say, a magnesium sulfide, right? And you say, great, I'll measure these two things. There's sulfur in both. The problem is that, of course, A has changed. And there's no way I can kind of group back because this is always B. And so it's not like I can kind of substitute this in A and then have some similar structure or something. So you can measure similar things all you want, but ultimately these are ratios. You can never find an independent one so that you can just kind of go to the periodic table like we do. We look up the radius of a particular ion and we say, aha, this one with this one, it's likely to form, it's likely to need tetrahedral coordination, and then it fits into these space groups, and that's why, it has this crystal structure. So we can't quite get there unless all we need to do is measure one, right? And then we're free, because then, of course, once you have, one particular ion radius or a couple, then you should be able to do this kind of analysis. And X-rays are extremely precise. You measure it to the degree of a thermal expansion or something, right, 10 to minus 6, which is pretty good. So how do we get somewhere else? We're going to have to measure something else, and we need to measure something that is related to the tightly bound electrons, right? Because remember, these ionic structures we're assuming are these billiard balls, right? And so what is that? Remember, that's a positive core. And then we have tightly held electrons around here. And we want to understand, in this situation, roughly, what is this size? Roughly. What is this sort of effective, radius about here? And that's not so easy to do, because a lot of times we'll talk about electronic properties, and we spend much of our time looking at the valence electrons, which are here, which do the bonding. We already mentioned ionic material. If this was an A, it gives up or accepts another electron and completes this shell. But it's this valence shell, actually, that is an enormous amount of concentration in looking at semiconductors and optical properties and everything else, because, of course, naturally, these are the ones interacting with the surroundings. They're the ones that become delocalized to make bonds. Drawing a neighboring one here. So it also has tightly bound electrons. And then there's the valence ones. And the valence ones are the ones that become delocalized, as we know, in more covalent materials. And they are responsible for quite a bit of the properties. Now, it turns out that in ionic materials, uh, uh, these don't interfere actually with an attempt to measure the tightly bound ones, because what happens is these extended ones end up being, very high energy. And so essentially that means that if they really want to kind of get extended, if this ion wants to really extend much of a true covalent cloud, it is, the band gaps are gigantic, and that makes sense, right? Because the potential on these guys is so high. And so really you're much, much closer to some minimum overlap and really just Coulombic type interaction, again, which justifies our looking at these things as ions. But in the context I'm talking about here, so the good news is that we're not going to have much valence cloud here. There's not going to be an extended thing that's dominating properties. We have an insulator. There's almost no conduction electrons because of that. So this purple here I've drawn extended doesn't exist. That's why these tend to be insulators. And that's all, really good. But still, it doesn't get me towards, well, how do I measure one of these a radius here? And you could tell where I'm going with this is that, well, we're going to have to measure something that's sensitive to the tightly bound electrons and then extract the volume somehow. And it turns out there's a few properties. If you look at tightly bound electrons and an ion-to-ion coupling, you're talking about the dielectric constant, which inherently is related to a few things. Index, which is essentially the dielectric constant in optical wavelength, and around optical wavelength, and also really this reduces to something which inherently is polarization. Because they are not free, there's restoring force, and so what we're talking about is an electric field comes through, these things get rattled, and maybe we can measure them. In fact, that is how you end up taking these measurements and then combining them. So I thought it'd be worthwhile to briefly go through just a little bit of this thinking, because it does come back again to our bonding curve, it comes back to our properties, and we want to understand all of this. And so I'm going to deviate in this lecture a little bit and talk about that. So here we have what we discussed before, just to give you a reminder that we have a 1 over r dependence of bonding and Coulombic related things, and then you have something that in the ionic case is looking like Coulombic repulsion, but remember there's other factors in there. And ultimately these potentials, which depend on 1 over r and things like that, ultimately combine to give you around R0, because the material is stable, and no matter what we do, it doesn't deviate much around here. We have thermal vibration, everything else, but it's in a parabolic pocket, and so the energy at the bottom is related with small deviations. This is assuming that R minus R0 is a delta and it's not too big. Then you end up with spring constants. So it means that if you try to move these atoms apart, it'll look like there are springs attached to them. And of course, that's going to be important as we go up, as I mentioned before, and connect to properties like, here I'm drawing ahead of time tensor notation for stress strain, right? So, so we have that picture where we have these ions and they're bonded to each other, but they have these electrons around them as well. And when I send an electric field in there, what do I see? And here's an experiment with 3 materials. Diamond, which is a diamond cubic structure with big band gap, still insulator. Sodium chloride, which we've talked about, ionic material, 6-fold coordination, and then a liquid, water, which has a high degree of polarization in the molecule itself. So if you remember, the oxygen is bonded like that, and there's a negative and there's a positive. They're all bonded, but the electron density is pretty much at the head of this thing. So, if I was to draw electron density, it'd be like, something like that, where, a lot of the electrons are hanging out on the oxygen. It's got a little tadpole-like feature to it. Okay. So the thing that I want to point out here is if we look at the index, which is an optical range, and we look at a capacitor, let's say we build a capacitance between two plates, and we, run essentially some sort of alternating voltage, we can extract the dielectric constant. Now remember, what we're talking about here is that if we were to look at the frequency range, these are both essentially just, here's my solid ions, got electrons around here, and what do I have? I have an electric field that is coming in here, switching direction and magnitude, right? So from an atom point of view, if I don't look at the motion, what do I see? I see a time variant electric field, right? So it's shaking these things, right? And there's going to be different things that respond to that electric field. And what we see at the optical end, this is way up there. I think if I recall, optical is roughly considered like, hertz or something, where this might be down by hundreds of hertz. So the frequency is completely different, right? In a way, you can't actually measure this frequency electrically. It's too high. That's why optical techniques are better. But remember, we're using the electric field inside the electromagnetic wave, and we achieve the same thing. So what we notice is that if we go to very low, let's say, 60 hertz, when you're standing in a puddle of water, what you find out is that we see on the electrical scale, actually I should put 60 hertz here, right? It's this one here, the electrical. You see a huge dielectric constant. If I look at n squared, which is essentially the dielectric constant in optical regime, all of a sudden, when I'm at 10 to the 14th or whatever it is, hertz, orders and orders of magnitude higher, I almost see no dielectric constant, something very small. In the case of sodium chloride, right, when I'm at a relatively low frequency, I see a higher dielectric constant than the higher frequency case of optics. However, it's not as big a difference as in the water case. And then finally, when I look at diamond, there's almost no difference between the optical and the electrical measurement, right? What this is telling us is that inside the material, in something like water, I have tightly held electrons around the nucleus, and so there's an electrical response to the field that's coming through. There is ionic polarization because these ions are connected by a spring, like I showed again in the last view graph, and so the electric field will tend to move things closer, move them apart as this oscillates back and forth, and then when it's changing, they're being pulled back with something that looks like a spring, right? And then, of course, in the water case, the molecule can turn, and that's called molecular polarization. So that's why you see this. You have three polarizations at low field because the frequency is low enough that all these can respond to it. And then when I go to very high frequency, it turns out what you're looking at here is only the electrical one, right? And of course, in diamond, it's only the electrical one. In sodium chloride, importantly for us, it's the electrical and ionic polarization. This means that through these studies, it may be possible to separate out the electronic and ionic polarization with frequency. You can see that we did it here. At low frequency, I see both. At high frequency, I only have the electronic. That should allow me to extract what each atom is looking like from a polarization point of view. And it turns out, when I do that, a fundamental thing of an atomic polarizability, there's a volume associated with it. And that allows us to understand different size ions at different crystals. Just a little background as to the time-varying properties of this. What you have in any of these cases, whether it's in the case of a electronic polarization, I have the nucleus, and what I'm doing is distorting the cloud a bit with the electric field. Let's say it biases it towards one side. And so I have this cloud, that's distorted that way. Well, what that means is this thing now is a dipole of minus and plus. So I have a little dipole. So that would be the case of electronic polarization. And then in the case of ions, a little more easy to see, this could be an ion pair, plus and minus inside the solid. So if that were the case, I'm looking at two ions with the spring again, and that would be the ionic case. So this is the lightest mass because these are tiny little electrons. This is the next heaviest because this involves the mass of ions instead of just a little electron. And then finally there's the case of water, where the molecule itself is a dipole, as I showed you before. If this is negative and these tend to be positive, there's an overall little dipole here, like that. Now, one of the common things you're going to start to see is this, at the smallest scale with only one charge, it's a dipole moment, and it depends on the charge and the distance they're apart, right? And so this means that distance, motion, the original position, and the volumes involved are going to be eventually extracted from these measurements. Now, if I look inside a solid, then it turns out that this is one of the key expressions. The overall polarization I see in Maxwell's equations is going to be some number of dipoles times their polarization, right? So, in other words, if I'm looking at ionic polarization, there's a number of dipoles that I have in the system, which in that case would be, let's say, a plus minus pair or something like that, or in the electron case, it's atoms, right? Because, in the case where the thing gets distorted like I had before, right, the number of these guys is a number of atoms, per volume. And in this case, it's the number of pairs per volume, right? So there we get to our volume again. And so that's written as the number of dipoles, and this is the electric field that's coming through. And here's the key thing, is A alpha, which is the polarizability. Okay. So this is ultimately how you get in a measurement to the volume, because you measure something that is P, but you know the density of things in there, which brings out the polarizability. The electric field tells you how much is being distorted, and you get a sense of how big the thing is. There are some details here that it turns out that the assumption here that P equals alpha E is actually only good if you have very isolated ions. So when you have a very high density, like in an ionic material, it turns out that the other ions shield it, but that can be corrected for its screening, essentially. So when you apply this external thing to a huge block of material, there's a local field that builds up that opposes the induced field, and you have to subtract that out from all the surrounding things to pull out what you want to look at locally. And it turns out that the local field is the external field plus, if you look at a spherical volume, so you'd want to find something that was anisotropic, something that is fairly isotropic in all directions, then it would be P over 3 epsilon 0. And the correction is, more substantial as we try to make materials anisotropic. But just for the argument, you can go and you can plug that back in to Maxwell's equations, which I'm showing you here. And when you plug that in and you put in the fact that the big P here is just equal to the local field, right? It's the local thing around those dipole moments with their polarizability and the number that I have. Then you end up with the expression that's really used to figure a lot of this out, which is the Clausius-Mosotti relation. And little v here is the volume per dipole. And that's how we can arrive at this. This is the real dielectric constant, and so we can measure this. And in a way, the left-hand side is the macro that you measure because it's dielectric constant, which is a macroscopic, Maxwell equation type thing. Where on the right side, we have a microscopic thing, which has the volume and the polarizability of the units. I've already mentioned this. I don't want to go into more detail exactly, but I just wanted to point out that the simple models for all this involve the fact that you have the response, it's F equals ma is the simplest way to model all this stuff. And then you have a drag term, which, there is usually some loss of energy. It turns out on an atomic scale, electronic polarizability has very little loss, and ionic has a little bit more, but very little loss. So you can this is very small. Then we have the driving force with the electric field coming by. And then this Kx, don't forget, is the spring force that tries to bring it back. So in any of these things, you have these expressions that tell you, as you get closer to critical frequency, how that driven oscillator, because remember it's a driven oscillator, you're driving it with electric field to be apart or closer than normal, but the restoring force, which is the spring, is trying to push it back. So you can imagine there's a critical frequency that if you drive it right at that frequency, it's going to blow up, right? It's like a driven oscillator at the critical frequency, which you guys should have seen before. And indeed that happens. What you see, and I'll sketch this out just for your own edification. Now this is for a generic material. No material has all of them in there. But what you'll see is if this is frequency and this is dielectric constant, remember water at low frequency had all of the things in there. So if you were to think about water as being the generic material, you have very high dielectric constant. And then at some relatively low frequency, the molecules stop rotating and the ability to absorb, this is what's used in your microwave oven, this transition here, because you try to pump it. Turns out that I'm drawing the real component of the dielectric constant. And the imaginary one is spiking here, and so you can deposit a lot of material, a lot of, let's call this W tau. This is the frequency for maximum imaginary coupling, the dielectric constant, the imaginary dielectric constant, all the power going into these rotating molecules. And because there's a lot of water and food, that's how a microwave oven works. Once we were able to build cheap microwave sources that were approximately this frequency, then you could deposit a lot of energy directly into the water molecules in the food and it heats it up. But of course, if you start to go too high a frequency, it's too fast for these heavy molecules and it falls off. And then you roll over and then you come to another critical frequency for ions and that spring constant, right? So with the spring constant, I drive this oscillator. It turns out, of course, it doesn't completely blow up. There's loss in the system, so you end up coming down like this, coming to a lower level. And then finally, you even get too fast for electrons eventually. There's a similar kind of thing there. And so when you're at the highest frequency, this is just 1. Basically, it doesn't see any material. It flies through the dielectric. It doesn't see electrons, ions, or anything. Here, of course, this is with epsilon electronic. And of course, important for us is in ionic material, you wouldn't have this huge rise, because this is from the molecular, and this is from ionic. So you can see here, if I'm playing with the ionic one, I can do measurements where I'm here. I can do measurements where I'm here. I can do measurements right here. This gives me epsilon real electronic, and this gives me the ionic plus the electronic, which you can't see anymore. But the point is, this gives me the both, and then I can know how much the ionic component is. And from all this, I can use a Clausius-Mosotti to come and extract the volume per dipole, which then I can use, and I can do that over a couple different material systems, get an idea how it changes with valence and things like that. And in so doing, I can finally now populate this thing after a lot of hard work with people long forgotten. I can come in here, and the atomic radius is given here. And so now it turns out the ion radiuses are different, so you'd have to look at sometimes if I have an ion that had 2 electrons pulled off of it, it's going to be much smaller, right? So I have to think about that. But in looking at simple things about Ra versus Rb, you can use these atomic radii and to estimate what kinds of crystal structures may form when I put them together. And you can see, of course, if you haven't looked at this before, in any column, because we're going down and adding more and more shells of electrons, the ions get bigger, of course. So in fluorine, if you look at this, what has a lot of electrons around it, it's 57, because it's even though it has a lot of electrons, it's not that many because the top of the periodic table. And it's got a very large, it's got a tight binding of those electrons. Whereas I come up, same thing, these are all tightly bound, but I have more shells, and so the ion gets bigger and bigger. And you can see iodine is like some huge ball, compared to like fluorine, even though both are categorized as, Bs, right? When we're talking about A and B, these are both the electronegative type, but fluorine is much smaller than iodine. And that's why calcium fluoride, if you look at it, it has, kind of an unusual crystal structure, because fluorine's in the far upper right corner. Yes, it's negative, but it's a small negative, right? And calcium is kind of a large, if you look, kind of a large A, right? And so that's why you end up with a lot more fluorine atoms around there than the calcium, CaF2. Okay, so that ends the substantial discussion of how we start to populate and what the rules are based on Pauling's first rule.